You probably just finished watching the first lesson on this unit 1.1 known as kinematics. So in that unit on inertia, you found that inertia and mass are essentially synonymous terms. We measure an object's inertia by measuring how many kilograms of mass that the object has. In that previous lesson, you heard about Newton's second law of motion, where he said acceleration is equal to the net amount of force impressed on an object divided by the amount of inertia, or divided by the mass, right? Acceleration is force divided by mass. And then we hinted at something known as the dirt equation, which I'd like to change into an equation that says displacement is equal to rate times time, right? Here we're using v, velocity, as a symbol that means the rate at which something's moving. So there's more to our study of motion than just displacement, velocity, and time. When an object has a force applied to it, then it's going to accelerate. So we need to relate these quantities. All right, so let's be clear what these symbols represent. Math is the language of physics, so in some ways it might seem like you're learning in a foreign language in this class if your math isn't up to snuff, but I'm going to guess you're well past algebra and trigonometry and have already dipped your toes into calculus here, so this should all be fairly straightforward. So we use the symbol delta x for displacement. So we're going to put symbol, meaning, how's that, quantity, and then I'll also add what units are used typically to measure it. So we could use inches for displacement, we could use miles, we could use feet. We're going to stick to the metric system and use meters as a way of measuring displacements. In fact, I'm going to, instead of calling it the metric system, I think I'm going to refer to it as the MKS system. In engineering, there's also something known as the CGS system. So the difference here would be the CGS system is based on measuring distances in centimeters, mass in grams, and time in seconds. We'll use the MKS system instead. We're going to measure distances in meters, mass in kilograms, and time in seconds. Okay, and then any combination of meters, kilograms, and seconds can form other meaningful units of study. For example, v represents velocity, and there's no single unit for measuring velocity. It's just a combination of meters and seconds, right? Your speed is how many meters you cover per second. We could use miles per hour, but we're going to stick to the MKS system. So T obviously stands for time. That would be measured in seconds. A stands for acceleration, and that's measured in meters per second. Per second, some of you might prefer meters per second squared, but for now, I'm going to call it meters per second per second. I have a hard time trying to figure out what a square second is. I know what a square meter is. I could buy a piece of wood that's 3 feet wide, a little more than 3 feet, 3.28 feet wide. That's a meter. By 3.28 feet long. And then, of course, I would have a square meter. I don't know what a square second is. So to measure something in meters per square second is not intuitive. But to say how many meters per second something increases its speed for each second that elapses makes sense to me. So I like to talk about meters per second as a way of expressing acceleration. Okay, so this is essentially what kinematics is. It's a set of formulas that we can use to relate displacement, velocity, acceleration, and time. But actually that list is a little short. Let me write it out one more time. We might have something like x subscript 0, we call it x naught. And then an x without that subscript. Same thing, we can have a t with a subscript 0, t naught, or just t. v naught and v, or a. And if there's a, what do I mean by this subscript? When we add this subscript 0 and call it t naught or x naught, that just means initial value. So this is a way of representing symbolically an object's initial position. Without the subscript, that represents final position. So if I take the difference between the two, then we can have a delta x, which is a displacement. Okay, so clearly an object's displacement is just found by taking its final position and subtracting from it the initial position. So the same thing, t naught is initial moment in time. The t without the subscript 0 is a final instant or final moment in time. So if we subtract the 2, we can get a time interval. But there's a trick to this. There's a little caveat here. You can't always have a reference system where an object's initial position is 0. Let's say you're running a race. Maybe you sign up on Thanksgiving for the turkey trot. So there's the start line. And then the finish line is somewhere in the direction the arrow is pointing. A lot of people showed up. They were very eager, and they lined up before the race very close to the start line. So there's a whole bunch of bodies in the way, and by the time you show up, there's all these other people, and you're standing here when the gun goes off and the race begins. So the 0 mark is at the start line, and your initial position when the race begins is not at 0. Now, maybe we can redefine what we consider the origin and just always say you exist at the origin. Okay, but if you want to compare your motion with somebody else's motion, you can't both have the same initial position, right? So we're not always going to be able to get away with saying initial position is equal to 0. If we could, then if this term right here is always equal to 0, then there would be no distinction between x and delta x. So here's what I'm getting at. We are allowed to almost all the time let initial moment in time be equal to 0. So when the starter's gun goes off, whether you're at the start line or somewhere behind it, the initial moment in time of the race is the same for one person and a second person, right? So if time interval is found by taking the final moment in time minus the initial, but we can pretty much always get away with saying the initial moment in time is at the 0 second mark, then there's no difference between delta t and t. And so for that reason, I'm going to drop this, and I'm going to drop the delta. And basically, t is going to represent both the final moment in time and the time interval. Okay? You can guess what v naught represents: initial velocity. And you can guess what v without the subscript is: that's final velocity. So if we take the difference between those, we can get a delta v, which would be a change in velocity. The change in velocity is nothing more than the final minus the initial. And then a represents acceleration. Now you might ask, why didn't I do an a naught and an a? Well, we're going to limit ourselves mostly to the study of objects whose acceleration remains constant. When a constant force is applied to an object, a constant acceleration results. Now, that's not always the case. You can have an object not only change position and not only change velocity and therefore accelerate, but you can have objects that change the rate at which they accelerate, and the rate of change of acceleration is referred to as jerk. We'll get into that. I don't want to get too far into this. So acceleration is not the same thing as change in velocity. It's certainly true that anytime something changes its velocity, it accelerates. The acceleration is more than just the change in velocity. It's how quickly the change in velocity takes place. In other words, we take the change in velocity and divide it by the time interval spent making that change in velocity. And of course, this is why the units for acceleration then are best expressed as meters per second per second. Velocity is measured in meters per second, time interval is measured in seconds, so there you have it. I won't get upset if you refer to it as meters per second squared, but hopefully you can appreciate why I prefer to say meters per second per second. So that's what kinematics is all about, a set of equations that'll relate all of these variables. And I'll just give them to you now, but we're going to spend some time in future lessons deriving these equations I'm about to list. So one equation says you can figure out what the final velocity of an object is by taking its initial velocity and adding to it the product of acceleration and time. You can find out the displacement an object has by multiplying the velocity it begins with times time and adding to that this other term, 1/2 at squared. Another way you can find an object's displacement is to take half of the sum of an object's initial and final velocity, and you might recognize that when we take two quantities, add them together and divide by 2, it's a way of taking an average. And if we multiplied an average velocity times time, we would get a displacement. There's another kinematics equation that says an object's final velocity when squared is equal to its initial velocity squared plus 2 times the product of acceleration and displacement. So this is a set of 4 kinematics equations. And much of the emphasis of this unit of study is going to be about putting these kinematics equations into practice. So that's all for now. We'll move on and define velocity and acceleration more formally in the next couple of video lessons. Thanks for watching.